I'm looking again at this log from Fliegertoni. There was one issue that you asked about in your original post that I didn't get to. You asked about a yaw and roll related issue. And I had just done a video talking about yaw and roll, and I had sort of run out of time in your video, so I kind of just threw the link at you for that other one. But you pointed out that you didn't think that the video I linked to applied. So I'm always interested in these yaw roll issues. It's one of the it's kind of fun to tune this coupling between these two axes and see what's going on there in a way that pitch kind of almost feels separate from yaw and roll in a way in terms of tuning anyway. But anyway, let's have a look and see if there's anything interesting there. And the first thing I want to do is I want to just show it. I couldn't download the video from Vimeo because I couldn't figure out how to do that. So I didn't look very hard though, so don't worry about it. But let's just see the issue. It's really extreme. There, wow, that's a lot of right roll, isn't it? Yikes! What happened there? Let's see if we can. Let me just go back again, and I'll play it again, and then we'll take a look at the log. Holy crap! Wow, that's really something. Let's have a look. Let's see what we can figure out. So here is that move. I believe it's that same move. I have up here on the top, I have yaw and throttle. Is that the same move? I thought you punched the throttle. I'm pretty sure it's got to be the same move. Let's look here. Let me turn the volume back on. No, 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 you don't. You don't raise the throttle at all. Okay, great. Yeah, I found the move. So I'm just looking at the throttle here, just I guess on principle. Here is your commanding left yaw. Okay, and let's take a look. First of all, we'll look at the yaw P IDs, and we see that, in fact, let me rearrange this just a little bit. Let's get yaw up here and the gyro, the yaw gyro. Gyro, hello, yaw gyro, where are you? Sorry, yaw gyro, there we go. And then, yeah, I feel okay about this. Let's get the roll gyro up here as well. Okay, yeah, I like that. So now, again, it is a little confusing in Blackbox that the roll and the yaw lines, they go the opposite direction. So when you yaw to the left, yaw goes positive, and when you roll to the right, roll goes positive. So normally we would kind of expect that in a coordinated turn, the lines would go the same direction. You're rolling left and you're yawing left, we would expect the lines to go in the same direction. That is not how they work. So when the yaw and the roll oppose each other, that means that you are coordinated. When the yaw and the roll go the opposite, well, go the same direction, it means that yaw and roll are not coordinated, that they're going opposite directions from each other. Yaw left, roll right, etc. So if we just look at what your copter did here, we can see that you started the move relatively flat. Then the copter rolled left. You see, so yaw is going positive, and that is left yaw. And because roll and yaw are opposite to each other on the graphs, this negative roll gyro indicates left roll. But then very quickly, it goes back the other way and rolls right. And corrects itself more or less. And by the way, now you move the stick, right? But in fact, we achieve zero angular rate. When the roll line is centered here, the copter is not rolling any direction. So what must have happened is you rolled to the right. Here, you're rolling to the right. You're still rolling to the right. You have stopped rolling to the right. But now the copter is like 45 degrees rolled to the right. And here's where you push to the left to fix it. So we see that when you do this yaw move, the copter begins to yaw to the left, and it continues yawing to the left during the whole move. And as it does that, it begins to roll to the left, and then quickly spins over and rolls to the right until finally the move is over. and that's when it stops rolling to the right. And that whole time, we can see that you didn't move your roll stick at all. So this is entirely something in the tune or in, I don't know, let's take a look. So what I'd really like to look at here is your roll PIDs, because of course you didn't command any roll at all. Therefore, what happened? So as the move begins, we can see the roll gyro, you begin to roll to the left, and that is uncommanded move. So you're yawing to the left and you're rolling to the left. Gyro is negative, roll gyro is negative. Since you are rolling to the left, and since you did not command a roll to the left, we should expect that the PID loop will push to the right and try and correct for the uncommanded move. What we see here is that P term goes positive, so the P term is opposing the gyro. The gyro is making a move that it is not supposed to be making because the stick is centered. The P term is opposing the move as it should. The I term also comes up and opposes the move. Okay, fine. And then, well, I guess that's successful because now it swings back the other way. Notice that P term is negative now. I term is still positive. So here we have a P term and I term that are opposing each other. And if this happens too much, you get a situation like this. So in this situation, the copter has rolled to the left when it wasn't supposed to, and the P term has tried to make it roll back to the right. Now it is rolling back to the right, but now it's rolling back to the right too much. It should have stopped. The P term was trying to stop the left roll, but instead of stopping it, it pushed too hard, and now the copter, instead of just stopping the left roll, now it's rolling right. The P term, as soon as that right roll starts, the P term immediately goes negative and opposes it, but the I term is still positive, and notice that the D term, the P term isn't moving. Let's have a look at your PID sum real quick. I already have an idea of what we're going to find. Let's see, PID sum roll. Yeah. Notice that the roll PID sum is 0. So from here to here, the roll PID algorithm is just not doing anything. The copter is rolling to the right. It is not supposed to be rolling to the right. The P term is trying to fight it, but the P term is being canceled out by the I term, and the actual PID sum is very close to 0. And then finally, the PID sum goes negative. The I term starts to decline, but it's already all gone horribly wrong, right? This is just the aftermath of the mess. And then eventually, when the move is over, things get cleaned up. So the first question that I think is important to ask is, why did the copter roll to the left when you began the yaw move? The reason that the copter rolled to the right is a separate question. And the question that I'd like to ask is, what do the motors do? And if we look at the motors when you begin the yaw move, these two motors slow down and these two motors spin up. And what we should see is that these two motors, the motors all stay in sync left to right, so the copter doesn't roll at all. But notice right here that these two motors are off. They've just gone to idle. And this motor is at full, and this motor is not quite at full. So this explains why the copter rolled to the left, because this motor was at full, and this motor was not at full, and these two motors are at idle. So there was more thrust on the right side of the copter than the left side, and that's why it began to roll to the left. Now the situation is trying to correct itself. Now we see that we're still doing the yaw, so this motor is off. This motor now is spinning up, trying to add more thrust to the left side of the copter. And now things are getting weird because now things are kind of messed up and the copter's doing all kinds of crazy stuff that it shouldn't have done. So the answer is that I think the answer is that you're asking too high of a yaw rate than your copter can really achieve. In order to achieve the yaw rate that you have commanded, these motors have to go completely to idle, And these motors have to go darn near to maximum. And in fact, let's just get this yaw out of here and let's add the motors. And we can see it. Here's the motors. The red motor maxes out. The blue motor mins out. And then the yellow motor mins out. The purple motor is the only one that doesn't max out. We're asking the copter to spin faster than it's really capable of spinning. So I think the answer here is that you need to reduce your yaw rate. That this copter doesn't seem capable of creating that much yaw rate without becoming destabilized. Now, as for whether you need to try and tune this situation, this is a pretty classic situation where we've got the P term and the I term interacting to cancel each other out. And the answer is either to reduce the I gain or increase the P gain. And I've talked about that in other videos, how those two interact and so forth. But I think the real thing is that if you reduce your yaw rate, then you'll find that this initial destabilization won't happen. And therefore, hopefully you won't need to tune out this destabilization here. Now you may be saying, what about all those other videos I've seen of pilots doing crazy pirouettes, crazy zippy, whatever, super fast 360 pirouettes? Clearly, it's possible to have a really ridiculously high yaw rate, and I agree with you. And I don't know what those pilots are doing differently, but it sure seems like your motors are maxing out and minimuming out. And once you've done that, once the motors max out, you'll always end up with some destabilization because you'll have a motor that needs to spin faster and it can't. So if a motor is spinning as fast as it can to create the yaw rate you're commanding, and then the motor needs to spin even faster to keep the copter stable on the roll axis, it's got no more to give. So you have to avoid scenarios as much as possible. You have to avoid scenarios where you are commanding the maximum rate, the maximum throttle value out of the motors. And you do that by keeping your rates low. And so the functions that will affect how fast those motors can spin and how much thrust they get out of them, that's a function of things like your battery rating. You're on 3S, for example. On 3S, the motors aren't going to spin as fast as they would on 4S. If you were on 6-inch props versus 5-inch props, again, the motors wouldn't spin as fast. And when it comes to yaw, I believe that you get better yaw performance with fast spinning, high pitch props. So 4-inch, 5x4.5 props, I think are, sorry, 5-inch. 5-inch. I said 4-inch. Well, 4-inch probably do even better, but I've never flown 4-inch. But 5-inch, 5x4.5 props, 2300 kV motors on 4S. That seems like a recipe for very good yaw performance. Whereas 3S with 60-30 props, that may be a recipe for mediocre yaw performance. The other thing I have to say is that when I went to high-end ESCs, when I went to Little B ESCs, and I know I sound like I'm pimping them all over the place, but what can I say? They just fly amazing. They fly so much better than the ESCs I had, which were F12A from Ready to Fly Quads. They were fine ESCs, but they were not great ESCs. Little Bs are great ESCs. And my yaw performance got so much better when I got good ESCs. And you're flying DYS 20A with BL Helis. Those are like my F12s. Those are fine ESCs, but they're not great ESCs. They're not world-class ESCs. I really feel like if there's a single thing people could probably do to get more performance out of their copter, it's better ESC. And then I kept talking for another minute or so until my recording cut me off, and I realized I was just babbling. So that's it. I've said my piece. Good luck and happy flying.